SwayamPrabha. Digital India. Educated India.
Hello everyone. So in the last class we were discussing the computational cost associated with direct numerical simulation, and we looked at the context of homogeneous turbulence because that was the simplest form of turbulence. We could easily analyze the cost associated with it. We could easily analyze the accuracy associated with it as well, especially since we are using spectral type methods. Pseudo-spectral methods to be specific, but because we are using spectral methods which are of infinite accuracy, they have zero truncation error, isn't it? That's why I say infinite accuracy. We are able to analyze the accuracy and the cost associated with it. So now that's what we are going to do. We are going to look at it in detail. What is the cost associated with doing a direct numerical simulation and how does that depend on the Reynolds number? So this part of the section where we talk about the computational cost, we had discussed this last class where we said the main numerical and computational issues have to do with the time stepping strategy, control of aliasing errors, and the implementation of distributed memory parallel computers. And Rogallo's paper in 1981 provides a detailed description of all of these issues, including the formulation and strategies and all that. Okay, but let's say our computational domain is this cube, right, of each side L, and you have to have a box size L that is larger than the integral length scale so that it can contain all the integral length scales in it. Now that, and also one additional requirement is that the grid spacing delta x within this box should be small enough to represent the dissipative scales, to resolve the dissipative scales. In a sense, it should be able to capture the Kolmogorov scale. Finally, there is also a delta t requirement, a time step requirement that is required to that should be small enough so that you are temporally accurate. All right. So now when we talk about delta x, where do we get these limits from, right? We know qualitatively it has to be large enough, okay? So the box size should be large enough to contain the integral length scale, and the grid size should be small enough to capture the Kolmogorov scale. But let's be more specific. So for isotropic turbulence, a reasonable lower limit for L is that it is 8 integral length scales. And why do we say that? We had done some estimates a few classes back when we saw how the energy containing range is sort of peaking between is sort of peaking at very low Reynolds numbers, very low wave numbers, of course, but primarily the 80% of the energy containing range is contained between 6 L0 and 1/6 L0. So this estimate is coming from there. That is, that a reasonable lower limit on L is 8 times the integral length scale. So 8 L11, which in terms of kappa naught is going to be kappa naught L11 would be pi by 4 or equal to 0.8. So this is something we did last class. Now the Fourier representation of the velocity field, because of the Fourier representation of the velocity field, you have to implement periodic boundary conditions. We know that. And we had also, when we did this analysis of this 80% of the energy being in between 6 L0 and 1/6 L0, we noticed that the peak of the energy spectrum is contained in kappa L11 equals 1.3, approximately equal to 1.3. And that 10% of the energy is contained below wave numbers kappa L11 equal to 1. So if you use kappa naught L11 equals 0.8, which is what we are planning to use, then approximately 5% of the energy in the energy containing range, in the low wave number range, right, in the energy containing range, that is not captured. You are missing out on 5%. You understand what I mean? So we saw that the peak of the energy spectrum was at kappa L11 approximately equal to 1.3. 10% of the energy is at wave numbers below kappa L11 equal to 1.0. Only 10%. The 90% of the energy is contained in wave numbers above that. Which means if you use something like kappa naught L11 approximately equal to 0.8, then you're missing out on 5% of the energy. I hope that is clear. So that is as far as the energy containing range. That is as far as the limit of L is concerned. The limit, as in the upper limit of your box size is concerned. Okay, that is your upper limit of the box size. Now let's look at the small scales, the delta X requirement. The resolution of the smallest dissipative motions are characterized by the Kolmogorov scale. We now know that the Kolmogorov scale is the smallest length scale, and you should have a sufficiently small grid spacing, and let's try to determine a ratio delta X over eta, so that whatever ratio we get, we now know that it will be that times the Kolmogorov scale is what your grid spacing should be. So delta X over eta, or correspondingly, what is the maximum wave number that you should be using, right? So delta X over eta, which would be the equivalent of kappa max eta, right? So a sufficiently large maximum wave number, kappa max eta. Now what is this? Now again, we had also looked at where the dissipation is maximum by looking at the dissipation spectra, if you remember, D of kappa. The dissipation spectrum was extremely small beyond kappa eta equals 1.5. It was just very small. And in fact, what we know now is that kappa max eta should be greater than or equal to 1.5. So that is a good criteria for a resolution that is required to capture all the scales, especially the dissipative scales. So that means if you do a grid spacing analysis, then delta X over eta, now delta X is going to be pi over kappa max, okay? Delta X is pi over kappa max, we saw that earlier. If I substitute that there, then I have pi over kappa max eta, and kappa max eta is greater than or equal to 1.5. So pi over 1.5, which is approximately 2.1, which means your delta X should be approximately equal to 2 times eta in order to capture all the scales. The Kolmogorov scale is the smallest length scale available, okay, is the smallest length scale available. Remember, this is all order of magnitude. We are not saying that the smallest length scale is going to be, if the Kolmogorov scale is say 1 mm, is going to be 1.0000 mm. It is order of magnitude. It is going to be in and around the Kolmogorov scales. The smallest scale we think is the Kolmogorov scale, but it is in and around the Kolmogorov scale. So what we are saying is that your grid spacing should be small enough such that it should be at least, the minimum value should be 2 times eta. Okay, so the minimum value should be 2 times eta is what we are saying. Now that means you are going to miss out on some dissipative motions. Yes, but that is going to be very small. Even when we started the statement, we said that the dissipation spectrum is extremely small beyond kappa eta equals 1.5. So beyond that, if you don't resolve, yes, you are missing out on some motions. Yes, you are missing out on some energy, but that is going to be extremely small. Just like on the smaller wave number range, when you're using kappa naught L11 equals 0.8, what you're saying is that you're missing out on 5% of the energy. You're not capturing that 5% of the energy. Fine. In the same way, here too, when you're using this particular criteria, say 2 times eta as your grid spacing, then you are going to be missing out on some dissipative motions, but very little. So I hope that is clear. So now, if I look at my 2 spatial resolution requirements, which is basically L over L11 equal to 8 and kappa max eta equal to 1.5. So these are your 2 spatial requirements. This determines the box size and this determines my grid size, the upper limit and the lower limit. So that will tell us what is the number of Fourier modes that are required. So here, if I want to find out n is going to be equal to 2 kappa max over kappa naught, and and I multiply by eta, I divide by kappa naught, which means I divide by eta, multiply by kappa naught, multiply by L11, divide by L11. I'm sorry, kappa naught was already there, so I don't need to divide and multiply by it. But what I'm doing here is, in this equation, is that I am dividing and multiplying by eta, I'm dividing and multiplying by L11, and I'm dividing and multiplying by L. Finally, what I get is, for kappa max eta, I put 1.5, and for kappa naught L11, I put 0.8, which is what I determined. Then I have all of this left, so I have 12 over pi L11 over L times L over eta. So this is what I have. So using now the model spectrum to determine L11 over L, the value of n is obtained to be a function of Reynolds number. So that is coming from the spectrum, L11 over L. At high Reynolds number, L11 over L has an asymptotic value of 0.43. So the above equation, what happens is, you will get n is approximately equal to 1.6 times L over eta. Okay, because this one has 0.43, you plug that in there, you will have 1.6 times L over eta. The L over eta, basically it is the integral length scale divided by eta. This we already determined it as an expression of Reynolds number, which is REL to the 3/4. So it will be 1.6 times REL to the 3/4. In terms of the Taylor scale Reynolds number, it is something else. So it would be 0.4 R lambda to the 3/2. So essentially n cube is now this whole thing cube. So that would be 4.4 times REL to the 9/4, or 0.06 times R lambda to the 9/2. So the total number of wave numbers to be considered is a function of the Reynolds number to the 9/4. Reynolds number to the 9/4, a positive power. So these Reynolds numbers are going to be pretty high. That means RE to the 9/4 is going to be a very large number. And we'll get some estimates for that. Now, I'm not going to go too much into R lambda, but we already have it in terms of the integral scale Reynolds number, which is what is more important to us. The Taylor scale Reynolds number, we haven't looked at it in a lot of detail because it's mostly applicable only to isotropic turbulence. It was determined for grid turbulence, and it is mostly applicable anyway only to isotropic turbulence. So we are not going to be considering that. But REL is a good estimate to look at. So this graph here shows how n varies with R lambda. And as you can see, although initially the curve is not as steep, the steepness sort of increases as you keep increasing R lambda. The dashed line here is the asymptotic curve. And on the left y-axis I have n, and on the right y-axis I have n cube. So n cube, for the three directions, we have to consider what n cube is. N is not sufficient enough, right? Because n will just give you, okay, what is the total number of wave numbers in each direction, whereas n cube will give you the total number of wave numbers in all directions together, and that will be a good estimate of what the computational cost will be. So this gives you an idea. We are talking about 10 to the 12 points at a R lambda of 1000, and R lambda of 1000 is a relatively high Reynolds number. Of course, it is a relatively high Reynolds number, but what also matters is this is actually more of a practical Reynolds number that is in the that is out there for different applications. So R lambda is equal to 1000 is turbulent, of course, and it is more of a practical Reynolds number that you see in a lot of applications. That means what you see here is realistic, 10 to the 12. We are talking about more than 1 billion points for a single calculation. So this gives you an idea, right? And so that is only with respect to the Fourier modes. In order to determine the total computational cost, there is one more aspect that we need to consider, and that is the time step. Because you are actually solving for the transient equations. You are actually solving it with respect to time. That means temporally also it has to be accurate. Every velocity field that you give is at a single instant in time. At the next instant, if you want it to be accurate, your time step should be small enough. It should be reasonable and to provide an accurate solution. So the advancement of solution in time should also be accurate. That means it is necessary that a fluid particle move only a fraction of the grid spacing in the time step delta t, right? It cannot move one full grid spacing or more than that. Then you will be temporally inaccurate. So one way to do that is to use the RMS velocity as an estimate. And the RMS velocity, the average of the RMS velocity can be just taken as square root of the turbulent kinetic energy. Square root of the turbulent kinetic energy multiplied by delta t divided by delta x. So this is essentially u delta t over delta x, u being the RMS velocity. And what we are saying is that that should be 1/20th. This is that fraction that we are talking about. Fraction of the grid spacing. So what we are saying is it should only move 1/20th of the grid spacing in that time step. That is what we are saying. So the duration of simulation is typically about 4 times the turbulent time scale. And the turbulent time scale is like an eddy turnover time, so k over epsilon. So the total number of time steps would be 4 times tau over delta t, where tau is the turbulent time scale, so k over epsilon. And then so that would be 80 times L over delta x, isn't it? That would be 80 times L over delta x, or 120 over pi L over pi, and that is approximately equal to 9.2 r lambda to the 3/2. It is 9.2 r lambda to the 3/2. So where did I get this 80 from? This 20 from here basically came in here, right? And your tau, so I have 4 tau over delta t, and what I'm doing is I am substituting for the tau, I'm substituting k over epsilon and everything in there, and then I'm getting this estimate of 80. Then I have 120 over pi L over eta. 120 over pi L over eta. So that comes from, I have for L and delta x, instead of delta x, I will put in a kappa, and I will put in 2 pi as well. So then I will have 120 divided by pi L times 8, L divided by eta. And then that comes out to be 9.2 r lambda to 3/2. Okay, so that is the total number of time steps. Now for the total cost. So to an approximation, let's calculate the total number of flops required would be total number of modes times total number of time steps. That's an approximation of the total number of floating point operations. So that would be n cube m. And your estimate for n cube that we determined earlier, and our estimate for m that we determined just now, all those, if you plug it in, you get 160 REL to the cube, which is 0.55 r lambda to the 6th. If you want to calculate the total time that is required on a gigaflop machine, you just need to divide this by 10 to the 9, because a gigaflop would be 10 to the 9 flops. So the time in days required to perform a simulation at a computing rate of 1 gigaflop is 10 cube n cube m divided by 10 to the 9, 60 times 60 times 24, isn't it? So that would be REL over 100 to the cube, or r lambda over 70 to the 6th. So this would be the time in days needed to perform a simulation at a computing rate of 1 gigaflop. And then that means this is what your estimate is. So you can look at a table here. This is on a gigaflop machine. So today we have exaflop machines. So this would be pretty much 9 orders of magnitude faster than a gigaflop machine. So everything in here can be divided by 10 to the 9 to get an estimate, right? So let's take a very high R lambda, which is about 800, and REL of 96,000, which is like a very practical Reynolds number. A gas turbine engine would be close to that, or in fact more than that, but it would be close to 96,000. The total number of grid points in each direction is 9218. The n cube is 7.8 times 10 to the 1. The total number of time steps is 21,000. N cube m is this value here. So in CPU time for a gigaflop machine, for a single gigaflop machine, it is 5,000 years. Now obviously that is impractical, and this is not something we can achieve either. But today this Reynolds number is somewhere in the vicinity of achievable, right? Because we are talking about a machine that is probably that is at least 6 to 9 times or 6 to 9 orders of magnitude faster than a gigaflop machine, today's machine. And we are talking about multiple machines because in parallel. So then this will definitely be in the vicinity of achievable. Am I being clear? Because you are dividing 5,000 years by 10 to the 9. So already you are now in days, and then you go into multiple machines, and then you can actually achieve this in days. So this data is of course from 25 years ago, but we still can use this to make an estimate of how long it will take for the DNS calculations. So I hope that was clear. If you see here, what we have done is we have estimated the computational cost, and we could do this because we had a periodic box. We had equal points in all directions. So n became n cube. We could estimate what the ratio of the largest length scale to the smallest length scale is. We could do this because it is homogeneous turbulence. We could come up with an estimate for L11 over L. That is, again, we could do this because it was homogeneous turbulence. All of these estimates, we could do it because it was homogeneous turbulence, because it was a simple kind of flow. All of this changes once you have inhomogeneous flows. We will discuss that actually in this module as well in the next class. But all of this changes when you have inhomogeneous flows. But one thing we know for sure, the timing is only going to increase because the complexity increases. You no longer have the same number of points in each direction. So coming up with an estimate of the computational cost is hard, yes, but it is definitely going to be higher than these estimates. So that is the reason why we chose a simple problem. We chose a relatively simpler method. When I say a simpler method, conceptually it is simple, right? Direct numerical simulation is conceptually simple because all it is doing is that it is solving the Navier-Stokes equations exactly. No other specification, no tuning factors, no other specification. So it's just a matter of solving those equations exactly on the right grid. And then that will give you that will give you the correct solution. So it was easier for us to do all this analysis in homogeneous turbulence and for direct numerical simulation. So what we have done here is now we have looked at all the criteria, right? We looked at the level of description, we looked at the cost and ease of use, the range of applicability and accuracy. And we compared the mixing length model and direct numerical simulation. And in this class, what we have done is we moved solely to direct numerical simulation. We saw how pseudospectral methods are used here. And within pseudospectral methods, okay, now based on the accuracy, based on what are the limits for the box size, what is the limit for the grid size, and based on those box size and grid size, we came up with an estimate for the cost. So that is what it was, right? We saw that the total number of modes, as you can see, is 12 over pi, L11 over L, and L over eta. Now this is what I was talking about. The L11 over L, we estimated it from the model spectrum. We couldn't do that for a very realistic flow. For a jet flow, coming up with an estimate of L11 over L is not easy. We can still do it, but it's not going to be that easy. It's going to be a very much rough calculation in something or more of a realistic flow. But because it is homogeneous turbulence, because we have a model spectrum available, coming up with a value for this is easy. And it turns out it has an asymptotic value at high Reynolds number, so which is 0.43, and we just plugged that in. Then it was just a matter of it being a function of L over eta, which we know how it relates to Reynolds number. We already did that earlier, where we had proved, and the equation we wrote at that time was that eta over L is of the order of magnitude of Re to the minus 3/4. And that is what we are using here. L over eta is REL to the 3/4. So we put that in, we wrote it as an estimate of R lambda as well, although I don't want you to focus on that too much because the Taylor scale Reynolds number is something that we hardly use. However, that said, the plot that we have shown here is n versus r lambda and n cube versus r lambda, and we have seen that we are talking about more than 1 billion points for an r lambda of 1000, which is closer to a very realistic Reynolds number in practical applications. Now, just calculating the Fourier modes was not enough, so we had to come up with an estimate for the time steps as well, because temporal accuracy is also important, right? So then we came up with an estimate for the total number of time steps that you will need to run, based on the idea that you will have to run probably for 4 times the turbulent time scale. So that gave us an estimate of 120 over pi L over lambda, or 9.2 times R lambda to the 3/2. And then you can get an estimate for REL as well. That is not shown here, but you can get that as well. Now, once you put everything in together, then what you have is you have REL over 800 cube, or R lambda over 70 cube. So that is the total number of that is the total computation time in days. And we put that into a table based on R lambda. So at a relatively low R lambda, we are like 25, even though you will find a lot of literature that has done calculations at R lambda equals 25, R lambda equals 50. Okay, they are considered to be turbulent, yes, but they are relatively low Reynolds numbers, and the turbulence is not that high. And in these cases for 25 and 50, as you can see, if you run it on a gigaflop machine, it takes hardly any time, 20 minutes and 9 hours and all that. Okay, but what we are interested in is the very high Reynolds numbers, which are more of practical applications, and they take a long time, but only on a gigaflop machine. Now, considering that we have much more powerful machines today, these are going to take much less time. So DNS is starting to be more feasible in today's day and age. So in the next class, what we are going to do is we are going to look at the limitations of these estimates and what this means for inhomogeneous flows, right? All of this we have looked at in terms of homogeneous turbulence. We know that homogeneous turbulence is not practical, but it's the simplest problem to analyze in terms of looking at turbulence on a fundamental level. And we are going to look at inhomogeneous flows in the next class. Thank you.